Good morning, grade 1S students. I hope you are doing well. Today I'm going to finish this chapter, Mechanical Waves. Please pay attention. I will remind you a little bit about waves. What are waves? Waves are rhythmic disturbances that carry energy but not matter. For example, water waves are not created unless there is something or a signal that disturbs the surface of water. And as the water waves move, they carry energy but not matter. The four major characteristics of waves are the amplitude, period, wavelength, and the frequency. Amplitude is the distance between the crest or trough to the equilibrium line. The period, represented by T, is the time taken for one complete oscillation, for one cycle. Wavelength, represented by lambda, the wavelength is the distance between the crests of one wave. And the frequency is the number of oscillation or cycles in 1 second. This is why we say that the frequency is represented by cycles per second or hertz, the same, because the SI unit of frequency is hertz. Classification of waves. Waves are classified according to the media of propagation into two groups, mechanical and electromagnetic. A mechanical wave is a wave that propagates in a material medium but not in vacuum. It requires a material medium. Vacuum is the space devoid of matter. However, an electromagnetic wave propagates in vacuum and other materials. For example, the light, microwaves, infrared, X-rays, ultraviolet rays, radio waves. We will see these in the next chapter. Light waves propagate in space to reach Earth. This is why we consider light waves as electromagnetic waves. They propagate in vacuum. What are the two phenomena associated with progressive waves? The two phenomena associated with progressive waves or traveling waves are reflection and diffraction. What is the difference between reflection and diffraction? Let's start with reflection. As a wave propagates along the spring, it reaches the end and then turns back and propagates in the opposite direction. All the waves are reflected when they reach the limit of propagation medium. All the waves, this means mechanical and electromagnetic waves, are reflected. However, they must reach the limit or the end of the propagation medium. Look at the first picture. When the propagating wave reaches the end of the spring, it doesn't stop. However, it turns back and propagates in the opposite direction. Look at the second picture. When the wave propagates and reaches the reflective surface, it turns back and propagates in the opposite direction. This is reflection. Reflection doesn't change the speed because the wave continues to propagate in the same medium. You can review the note in the previous video. In general, speed is equal to wavelength times frequency. If the speed is constant, then the frequency is also constant. Number 2, refraction. Refraction is the path of a wave from a medium to another. For example, when light waves cross air to water. If the direction of the wave is not perpendicular to the limit, for example, as seen in the picture, the wave changes in its direction. During refraction, the wave changes its speed, however, the frequency remains the same. Note, when the speed changes, the wavelength also changes. So observe the figure. Here we have a light wave. This light wave is crossing air to the water. So what happens? Since the incident ray is not perpendicular to the boundary or to the limit, the wave changes in its direction. As it changes, the speed changes, the wavelength changes, however, the frequency remains the same. This is the characteristic or a property of refraction. Let's correct this exercise. Suppose a motorboat makes waves while traveling across the surface of the lake. Also, the waves travel towards the shore shores at a velocity of 1.5 meters per second. So here, velocity is given, or the speed. Furthermore, the distance between the wave crests is 2 meters, so lambda, or the wavelength, is also given. Calculate the frequency. First, write the general formula. Speed equals wavelength times frequency. Then find frequency. Frequency equals speed divided by lambda, so 1.5 meters per second divided by 2 meters equals 0.75 waves per second, which is the same as hertz. Exercise number 3. Suppose the speed of sound is about 300 meters per second and the frequency of the wave crest is 15 cycles per second. Okay, we have frequency 15 hertz, we have the speed velocity 300 meters per second. Find the wavelength of the sound waves that it creates. Write the general formula. V equals lambda times the frequency. In this question, you must find lambda, so lambda equals V divided by frequency. So 300 meters per second divided by 15 cycles per second, or 15 hertz, equals 20 meters. So the wavelength of the sound wave is 20 meters. Exercise 4. Specify which of the following figures represents waves of higher frequency. Frequency equals 1 over t. So frequency and the period are inversely proportional. As the frequency increases, the period decreases, and vice versa. Let's see these two figures, figure 1 and figure 2. So in figure 1, we have period 1, and in figure 2, we have period 2. So let's compare period 1 and period 2. Period 1 is much smaller than that of period 2, so the frequency 1 is much higher than frequency 2 because the frequency and the period are inversely proportional. Please open your books, page 147, and let's solve number 2. Given that the frequency equals 76 beats per minute, find it in SI unit. SI unit means hertz. So hertz represents beats per second or cycles per second. These are the same. So how do we convert 76 beats per minute to beats per second? Put it. 76 beats divided by 1 minute. Convert minute to seconds, so times 60. And the answer will be 1.3 hertz or 1.3 beats per second. Today's session is finished. Please, I want you to review all this chapter.